Delta H is something new that we've been working with, and it represents the potential energy of a whole system. So in a reaction, we have potential energy from the chemical bonds that are present in the reactants. And as a reaction proceeds, those chemical bonds change and the potential energy of the system changes as well. So the delta H represents this change in potential energy in the system. Something that is negative is exothermic, as in it's producing excess heat. The potential energy is being converted into heat. And something that is endothermic will be positive, where the potential energy is increasing, therefore heat is being absorbed. So, the reaction of calcium metal with water is one that you're familiar with. Here's the balanced chemical equation. And we can see the graph here. So we see that our two reactants, calcium and water, start at a high potential energy up here, and they go down to a low potential energy here. So that tells you that the products are more stable, and that the reaction here is losing energy because it's decreasing in potential energy. So we're going to put our delta H value on the graph. Put it right next to the slanted line, because that is showing the change in our energy here. Provide an explanation for why or how the products have a lower potential energy than the reactants. Start off with two reactants, calcium and water. Water is very stable. It's stable and low in potential energy. But our calcium metal is very unstable relative. We do have calcium metal that exists, obviously, in the world, but unstable in terms of how relatively stable it is. So relatively unstable, high in potential energy. So that means that when calcium turns into calcium hydroxide, which forms a salt, which is a more stable form, it's going to lower in potential energy. Even though water is relatively stable, the overall change for calcium to calcium hydroxide is going to be so large that this is going to be an exothermic reaction. It's going to go from something that is relatively unstable to something that is relatively very stable. This profile indicates an exothermic reaction. In exothermic reactions, heat is produced. In other words, you'll start off with something that's room temperature, and then you'll end up with this like hot, soupy, white suspension at the end. So which of the following choices best explains where the heat comes from? So does the heat come from the atmosphere? Well, that wouldn't really make sense, because if you had a beaker just sitting there in the atmosphere, while it's just sitting there, the temperature outside is also going to be the temperature inside. So there would have to be some sort of heat lamp or sudden burst of energy from the outside. So that doesn't really make sense. The heat comes from the potential energy originally present in the calcium metal. Now this one makes sense. We have something that is high in potential energy going to something that is low in potential energy. And as we know, energy must be conserved. So that energy can't just disappear. It has to go somewhere. So it's converted into heat. The heat comes from the hydrogen gas. Doesn't really make sense, because if you'd have to get to the gas first, and the gas would have to heat up, and I'm not quite sure how that would work. Which of the following statements correctly describes the amount of heat produced in the reaction? This number here is describing the change in potential energy. Remember that potential energy is relative. It can be positive or negative. It can be all positive or all negative. It's relative to this baseline of unbonded atoms are 0. So this is showing that it's losing potential energy, and that's being converted into heat, to the same amount of heat, but it's important to know that heat is always a positive number. can't have negative heat. So it's always a positive number. Even though in the delta H it's negative, when we're talking about the amount of heat that's produced from the reaction, it's always going to be positive. The delta H value for the reaction shows that the reaction will convert 415 kilojoules of potential energy into heat if a complete mole of calcium metal is reacted. So, most chemists don't use such large amounts like that. Suppose you reacted 4 grams of calcium instead of a whole mole. How could we calculate the amount of heat produced? So again, I'm going to do this with dimensional analysis and then I'll show a proportion. We'll start with what we're given. 4 grams of calcium. First thing to do is to convert that into moles because we want to be able to use this conversion factor here. 415 kilojoules of energy for a mole. So that means we need our units to be in moles if we're going to get to kilojoules. So we have 1 mole over 40 grams of calcium, because that's how many grams are in a mole. Then we can use our other conversion factor, 415 kilojoules per mole. You can see here that they cancel out: grams, grams, moles, moles. And we end up with 41.5 kilojoules produced. If you want to do this as a proportion, you'd have to do 2. 4.0 grams of calcium over X moles is equal to 40 grams of calcium over 1 mole. We end up with 0.1 moles, and then we use that for the next one. 0.1 moles over X kilojoules is equal to 1 mole over 415 kilojoules. So it'll get you the same answer.